Okay, so in this video, we're going to be going over stress transformation. So this is kind of when we take an element from a certain element from a piece of, let's say maybe we had a cylindrical bar, right? And maybe this bar had certain loads applied to it. So what we're doing here is we're just taking a tiny piece of that, right? And then we're going to represent it like this over here. So we're going to call that the state of stress. So we're going to have two normal stresses acting on it. So we're going to have a sigma x and a sigma y, and then there's going to be a shear stress tau xy. So this is going to be just one plane, called the state of stress, how we represent this. And these are the positive sign conventions. So these positive signs. So we're going to have positive signs on our little diagram here if we have our normal stresses acting out of the body. So that's going to be tension. And the one that's kind of tricky is going to be if our shear stress is positive or negative. So what I usually do is I'll look at the right side, and if my shear stress arrow is going up, then it's positive. If I was looking at the right side, my arrow was going down, so in this case it's going up, right? Then it would be negative. And so your shear stress on each side of these, they always have to be equal and opposite. So if you have one going up on the right, you'll have one going down on the left. So this is the positive sign convention here. And you can imagine, right? So let's say we took this element on the left and we rotated it by some angle theta, right? So we rotate it by some angle theta. These stresses, right, the normal stresses and the shear stress, these values would change, right? And so we can use stress transformation equations to calculate what those new values are going to be. So another sign convention to note is that for this angle here, theta is going to be positive if we rotate it counterclockwise. So in this case, we're rotating it counterclockwise. So this is going to be a positive angle. And we do need to keep track of these. So our general transformation equations are here. I wrote them out. And we can calculate. So for example, our new normal stress in the x direction, that's going to be this sigma x prime. This should be prime, right? Tau xy prime, right? And this can be this equation. And sigma y prime is going to be this equation on the bottom here. So you can imagine, right, as we move these are going to change, but there's going to be some angle theta, right? At some point as we rotate this and we keep rotating, there's going to be some angle theta where our normal stresses, so our sigma x prime and our sigma y prime, are going to be at their maximum or minimum, depending if they're positive or negative. So we call this point where our normal stresses are maximum is called the principal stresses. So if we go down here, I wrote out the equations to calculate what our principal stresses are going to be. So if we want to find the orientation, so that angle, we want to find the angle. So that's going to be, we're going to call that angle where the principal stresses are acting, call that sigma p, right? So that's going to be the angle. If we come back up here, we rotate this and these are maximum, right? These two are maximum. So we can use this equation here, tau xy over sigma x minus sigma y divided by 2. That's going to have two roots. So you're going to have two answers for that. So you're going to have two different angles. So these two angles, so theta p1 and theta p2, those are going to be 90 degrees apart. Right, so this here is to find the orientation. This equation, which is sigma 1, 2, these are going to be to find the actual stresses, so the values of the stress. So the maximum and minimum. So they could both be positive, both be negative, or a lot of times you're going to have one positive, one negative, which means you're going to have one in tension, one in compression. So we use this equation here to calculate that. And you'll have, again, you have this plus or minus here. So you're going to have one answer that's big. We usually call that one the sigma 1, and then one answer that's small, which is going to be sigma 2, which is either smaller or negative than the first one. There's also, think about going back up here, right? There's also going to be some angle where our shear stress is going to be at its maximum. So one more thing to note about the principal stresses is here, when we have principal stresses, the shear stress is going to be 0 here. There's not going to be any shear stress acting when we have our angle where we have principal stresses. So that's an important thing to note. So there's no shear stress there. But there's also going to be a different angle. We call this theta subscript s, where our shear stress is going to be maximum. So now we're looking for an angle where we have this maximized here, our shear stress. So that equation, these are listed here. And it's also going to have two roots. They're going to be 90 degrees apart. And to calculate the maximum shear stress value, we just use this equation. So one more thing that's important to note here is that the maximum shear stress is going to be 45 degrees apart from the principal stresses. So wherever we have our theta P1, our theta S is going to be 45 degrees apart from that. And that's kind of just an overview of what we're going to be doing. There's also another way to do this called Moore's circle, which if you kind of look at these equations, they kind of look like equations of a circle. So we'll get into that, but we're going to do a couple examples.